A car factory that built luxury sedans for over a decade just went completely dark. Not because of a recall, not because of falling demand, because the company that owns it tore out the entire production line on purpose to make room for something that has nothing to do with cars at all. No name yet, no confirmation of what's replacing it. Just an empty factory floor where thousands of vehicles once rolled off the line every year. That factory belongs to Tesla, and what's replacing it might be an even bigger bet than anything the company has attempted with its cars. During Tesla's Q2 2026 earnings call, Elon Musk confirmed something most people weren't expecting quite this soon. Tesla has officially dismantled an entire vehicle production line to build its first dedicated factory for a humanoid robot. So why would Tesla sacrifice a working car production line for a robot that isn't even fully proven yet? What exactly is happening on the Cybercab production line that Musk says looks less like a car factory and more like, in his own words, a money printing machine? And just how far away is Tesla's humanoid robot program from actually shipping to real customers? Stick with us, because this update touches two of the boldest bets Tesla has ever made, and both of them just took a major step forward. Before we go further, make sure you're subscribed to Tesla Tech, because we break down updates like this, the ones buried inside hours-long earnings calls, every single week. There's a lot to unpack here, so let's get into it properly, starting with exactly what Tesla revealed about the future of that empty factory floor. Where Tesla stands right now. Before diving into robots and radically new production lines, let's ground this in context. Tesla just wrapped up its Q2 2026 earnings report, and the company remains one of the largest automakers by market value in the world, despite increasingly intense competition. Tesla delivered well over 1.5 million vehicles globally last year, with the Model Y and Model 3 continuing to rank among the best-selling vehicles on the planet across multiple major markets, not just within the EV category specifically. Tesla's manufacturing footprint spans Fremont, California, Austin, Texas, along with gigafactories in Nevada, New York, Berlin, and Shanghai. The Fremont factory in particular has a long history. It's the original Tesla vehicle plant, previously producing the Model S and Model X for well over a decade. That history is exactly what makes this next development so significant. According to Musk, Tesla has now dismantled the Model S and Model X production line at Fremont entirely to make room for the company's first dedicated Optimus humanoid robot production line. This isn't a future roadmap slide in an investor presentation. It's a physical, already completed conversion of a working automotive plant into a robotics factory. Is Tesla still, fundamentally, a car company? Increasingly, the honest answer is that Tesla is trying to become something broader. An energy, software, robotics, and vehicle company operating under one roof. And this factory conversion is one of the clearest physical signs of that shift yet. It's worth remembering just how significant Fremont has been in Tesla's history. This is the same plant where Tesla nearly ran out of cash during the early Model 3 ramp-up. The same plant Musk once described sleeping on the floor of during what he later called production hell. Converting a portion of that facility away from vehicle manufacturing entirely, rather than simply adding robot production alongside existing car lines, tells you something about how much internal priority Tesla is now placing on Optimus, relative to even its most storied model lines. Introducing the technology, Optimus Gen 3, and the Cybercab production line. So what exactly did Musk reveal during the earnings call? Two major manufacturing stories, both tied to Tesla's push into fully autonomous products. The first centers on Optimus, Tesla's humanoid robot program. Musk confirmed that production has officially begun at Fremont using Optimus Gen 3, and he even referenced an upcoming Gen 4 version during the call, while cautioning that the initial production ramp will be slow and deliberately gradual. In other words, Tesla isn't attempting to produce hundreds of thousands of robots immediately, because doing so simply isn't realistic at this stage. Instead, the early phase will focus on validating the production line itself, fixing design issues as they emerge, evaluating how well components hold up under real use, and collecting real-world operating data. Importantly, the first Optimus units built at Fremont won't be shipped to customers right away. Instead, Tesla plans to deploy them internally through a program it's calling the Optimus Academy, a controlled training environment where the robots perform tasks, make mistakes, receive corrections, and continuously generate fresh data to feed Tesla's neural networks. This matters enormously to Tesla's broader strategy, because the company doesn't want Optimus to simply execute pre-programmed movements. Tesla wants users to eventually be able to give the robot an entirely new task it has never explicitly seen before, and have it observe the situation, reason through the steps required, and complete the job independently, without engineers writing custom code for every single possible action. The second major story from the call involves the Cybercab, Tesla's dedicated two-seat Robotaxi, and specifically the production line Tesla has built for it at Giga Texas. Musk described the line in strikingly confident terms, suggesting that seeing it in person helps explain why he believes Tesla could eventually produce millions of Cybercabs every year. Despite the Cybercab being Tesla's simplest vehicle to date, featuring more than 50% fewer parts than a Model 3, no steering wheel, no pedals, just 2 seats, and a large open cargo area, the production line built to manufacture it is, according to Musk, unlike anything Tesla has built before, and arguably more advanced than any automotive production system currently operating anywhere in the world. Design details. Rethinking both a robot and a robotaxi. From scratch. Let's start with Optimus, because the underlying design philosophy here is genuinely fascinating. During the Q2 call, Tesla's head of AI software, Ashok Elaswamy, explained that Tesla is training Optimus using a strategy directly borrowed from its full self-driving program. The basic principle: the input is pixels, and the output is control signals. For a car, cameras capture lane markings surrounding vehicles, pedestrians, and other road users, and a neural network decides whether to steer, accelerate, or brake. With Optimus, that same underlying principle applies, except the range of possible actions is dramatically more complex. The robot has to not only recognize what it's looking at, but determine exactly which object to grasp, how much force to apply, how to move its hand through space, and how to adjust its grip in real time if an object begins slipping from its fingers. To train this level of dexterity, Tesla is drawing on multiple sources of data. The first comes from Tesla employees physically performing tasks, while robots observe and learn through imitation, with a more specialized internal team creating higher quality, higher resolution demonstrations to refine that training data further. The second source is genuinely unconventional for a robotics company: internet video. Musk has mentioned on multiple occasions that Tesla intends to train Optimus using publicly available how-to and instructional videos from platforms like YouTube, tapping into an enormous existing library of people cooking, repairing equipment, organizing inventory, using tools, performing countless everyday tasks. If a robot can genuinely learn a new skill just by watching a video the same way a person might, Musk argues that gives Optimus a form of task extensibility that could dramatically accelerate how quickly it acquires new capabilities. That said, it's worth being clear that watching a video doesn't automatically translate into robotic competence. Tesla still has to build systems capable of converting what a person effortlessly does on screen, like picking up a cup, into the precise coordinated movement of a robot's shoulder, elbow, wrist, and each individual finger. That's exactly the gap the Optimus Academy program is designed to close, generating real-world physical data that Tesla can then feed back into improved AI models and redistribute across its entire robot fleet through software updates, so that experience gained by one group of robots effectively benefits every robot in the fleet. Musk also introduced a genuinely interesting concept during the call: the idea that a large-scale digital Optimus could become a reality before a large-scale physical Optimus fleet does. A digital Optimus wouldn't necessarily need a physical body from day one. It could exist first as a virtual agent, processing information, interacting with software, and developing reasoning capabilities in a simulated environment, with those cognitive skills later transferred into a physical robot. This effectively splits the Optimus challenge into 2 separate problems: intelligence, which can be trained at massive scale digitally, and physical durability, which has to be validated much more slowly because it depends on real-world factors like materials, temperature, friction, mechanical wear, and repeated impacts that simply can't be simulated with perfect accuracy. On the Cybercab side, the design details are just as deliberate, though aimed at a completely different goal. Tesla built the Cybercab from the ground up around a manufacturing philosophy Musk has referenced before, called the unboxed process. Rather than assembling the entire vehicle sequentially on one long production line, the way cars have essentially been built for more than a century, Tesla breaks the Cybercab down into large modules that get completed in parallel. The front section gets assembled in one area, the rear section somewhere else, and the doors, exterior panels, floor, battery pack, seats, and interior each get handled on separate branches of the production system, all coming together only at a final central assembly point. With this approach, different sections of the vehicle stay open and accessible for much longer during the build process. Robots and technicians can reach components from multiple directions at once. Seats can go into the floor module before the upper body is even closed up, and wiring can be run while each module is still easy to access, rather than snaking wires through a nearly finished shell. Exterior body panels don't need to be installed early either, which means they're not exposed to scratches or damage during dozens of subsequent assembly steps. A simple way to picture it: Instead of building an entire house from the ground up in one continuous sequence, you finish each room separately, then bring the finished rooms together to form the completed house. That approach sounds elegant in theory, but it's also exactly why the Cybercab production line has taken years longer than expected to get running. Assembling individual modules isn't the hard part. The real challenge is getting every module to the point of final integration at precisely the right time, in precisely the right position, with tolerances that leave almost no room for error. Tesla first introduced this concept back in 2023, and it wasn't until 2026 that the company managed to complete roughly 70% of the full production line, after spending more than 3 years calculating the exact speeds, ratios, and millimeter-level tolerances required for every module as the system operates. Even now, according to Musk, the system still isn't fully finished, which is part of why Cybercab production hasn't ramped as quickly as some initially expected. Battery, powertrain, and technical specs for Optimus, the powertrain conversation looks nothing like a vehicle's, but it's arguably just as demanding an engineering problem. Musk described Optimus as being designed to achieve dexterity comparable to, or even exceeding, that of the human hand, an extraordinarily ambitious target, since the human hand combines significant strength with remarkable fine precision simultaneously. The robot needs to be strong enough to lift heavy objects, yet gentle enough not to crush something as delicate as a glass. And it has to maintain a firm, stable grip on tools while still remaining safe to operate in close physical proximity to people. There's also a genuinely serious safety dimension here that Musk addressed directly. Optimus weighs around 154 pounds, and if its control system became unstable or if the robot suddenly lost power, it could collapse right where it's standing. That's why Optimus's reliability isn't just about delivering a smooth user experience, it's a fundamental safety requirement. Tesla has to ensure the robot can detect faults, halt its movements, maintain balance, or shift into a safe resting state before a minor glitch has any chance of becoming an accident. That's precisely why the first Optimus units are being deployed internally under close supervision, rather than released directly to the broader public, giving Tesla time to catch failure modes before they ever reach a customer's home or workplace. All of that computing power, the perception system, the reasoning engine, the real-time motor control, has to fit entirely inside a humanoid-sized body. That means Optimus's onboard computer has to deliver strong performance without generating excessive heat, drawing too much power, or adding enough weight to compromise the robot's overall efficiency. Every watt spent on computation is a watt not available for actually moving the robot, so Tesla has to balance computational performance, thermal management, weight, and battery runtime all at the same time, none of which can be optimized in isolation without affecting the others. On the Cybercab side, technical specifics remain more conventional, but no less important. The Cybercab is expected to rely on Tesla's 4680 cylindrical battery cells, the same cell format already used in the Cybertruck and newer Model Y variants, chosen for its favorable balance of energy density and lower manufacturing cost at scale. Combined with a structural battery pack design, where the battery itself becomes a load-bearing part of the vehicle's chassis, Tesla is aiming to strip out as much unnecessary mass and complexity from the vehicle as possible, consistent with the Cybercab's broader design goal of being Tesla's simplest, most cost-efficient vehicle to manufacture: range, charging, and operational uptime. Because both Optimus and the Cybercab are designed around near-continuous operation rather than occasional personal use, range and charging looks a little different here than it would for a typical passenger car review. For the Cybercab specifically, expected range sits in the 200 to 300 mile territory per charge, which is more than sufficient for the kind of repeated short to medium urban trips a Robotaxi fleet vehicle would handle throughout a working day. Charging would rely on Tesla's existing supercharger network, which now includes more than 60,000 stalls worldwide, with the newest V4 superchargers capable of adding well over 150 miles of range in roughly 15 minutes. For a vehicle whose entire business case depends on maximizing time spent earning fares rather than sitting idle, fast and predictable charging isn't optional. It's central to the whole economic model. Tesla has also revealed a genuinely clever piece of infrastructure built specifically around keeping Cybercabs road-ready, an automated cleaning and servicing system. If food gets stuck on the seats, trash accumulates on the floor, or mud blocks one of the exterior cameras, the vehicle can become effectively blind in that area and unsafe to operate. To solve this, Tesla is developing a two-layer cleaning approach. The first layer operates while the vehicle is actively out on the road. Small cleaning nozzles positioned near the cameras can spray washer fluid or compressed air the moment sensors detect dirt or debris, functioning essentially like a windshield wiper built specifically for the vehicle's eyes. That means a Cybercab doesn't necessarily need to return to a hub every single time a camera picks up a bit of dust. The second, more substantial layer happens at dedicated service hubs, where Cybercabs can recharge, undergo inspection, and get properly cleaned. When a vehicle finishes a trip or needs a deeper clean, it drives itself back to the hub, the doors open, and a large robotic arm, similar to the kind used on industrial factory floors, reaches into the cabin. That arm automatically switches between different attachments, one for vacuuming up trash, dirt, and food crumbs, another using a gripper to remove bottles or bags left behind by passengers, and a soft cleaning pad for wiping down seats, door handles, and the touchscreen without scratching any surfaces. From there, dedicated indoor washing stations, not ordinary drive-through car washes, but facilities purpose-built for the Cybercab fleet. Clean the entire exterior, including wheels and hard-to-reach areas, before the vehicle recharges, completes a quick technical inspection, and heads back into service. Tesla has even suggested it could charge passengers an additional cleaning fee for excessive messes, as a way of encouraging riders to treat shared vehicles more carefully. How this compares to the competition? Tesla obviously isn't operating alone in either of these categories, and it's worth being fair about where the real competition stands. In humanoid robotics, Figure AI has emerged as one of the most closely watched rivals, having secured major partnerships, including a widely publicized collaboration with BMW to test humanoid robots in actual automotive manufacturing environments. Figure has focused heavily on rapid iteration and has demonstrated increasingly capable warehouse and light industrial tasks, though at nowhere near the production scale Tesla is now attempting at Fremont. Boston Dynamics, now backed by Hyundai's ownership, brings by far the longest track record in advanced legged robotics of any company in this space, with its Atlas platform demonstrating extraordinary physical agility in demonstrations for well over a decade. Boston Dynamics has generally prioritized mechanical sophistication and movement capability over near-term mass manufacturing, which puts it in a genuinely different competitive lane than Tesla's mass production first approach. Chinese robotics maker Unitree has taken yet another path, focusing on aggressively lower price points for its humanoid platforms and already selling robots commercially at a fraction of what competitors typically charge, which could make it a serious volume competitor if it continues improving general purpose capability rather than remaining focused primarily on research and entertainment applications. Agility Robotics, maker of the Digit robot, has already secured real commercial deployments in warehouse logistics settings with companies like Amazon subsidiaries and GXO, giving it a meaningful head start in proving out actual paid, real-world commercial use cases rather than internal demonstrations. On the Robotaxi and autonomous vehicle side specifically, Waymo continues to lead in real-world driverless ride-hailing experience, completing well over 100,000 paid trips per week across its active markets, using a LiDAR and camera sensor approach that many engineers consider more thoroughly validated than Tesla's camera-only strategy, at least based on current operating history. And BYD remains Tesla's largest global rival in overall EV production volume, continuing to expand aggressively across both passenger and commercial vehicle segments. So, has Tesla already pulled ahead in either category? Not conclusively, and it would be misleading to claim so. Boston Dynamics still has more raw mechanical sophistication in its robots. Agility Robotics already has real paid commercial deployments running today. Waymo has vastly more real-world autonomous driving miles logged. What Tesla brings to both races is something distinct, an attempt to apply true mass manufacturing scale and vertically integrated in-house engineering to categories that, so far, have mostly been produced in far smaller volumes by companies without Tesla's automotive manufacturing background. It's also worth noting how differently each competitor is approaching commercialization, because that shapes how directly they actually compete with Tesla. Figure AI and Agility Robotics have both prioritized landing paying industrial customers early, even at smaller production volumes, essentially proving out the business case, one warehouse contract at a time. Boston Dynamics has historically prioritized showcasing what's mechanically possible, often years ahead of any clear path to mass production. Unitree has gone the opposite direction, prioritizing low cost and high unit volume even before general purpose task capability fully catches up. Tesla's approach? Building the entire manufacturing pipeline for hundreds of thousands or millions of units before broad commercial deployment is arguably the riskiest of all these strategies, but it's also the one most consistent with how Tesla scaled its electric vehicle business in the first place. Tesla's long-term strategy. So where is all of this actually heading? For Optimus, Musk was candid during the call that the robot represents both Tesla's biggest potential product opportunity and, in his words, the most difficult product the company has ever had to scale. The reason is straightforward. Most of Optimus's components are entirely new. When building a car, Tesla can source parts like glass, tires, mirrors, seats, and body panels from a well-established global supplier network built up over decades. With Optimus, Tesla can't simply order millions of compact actuators, highly dexterous robotic hands, or custom circuit boards purpose-built for a humanoid body, because that mature component ecosystem simply doesn't exist yet at mass production scale. Musk described Tesla as essentially having to build Optimus's entire supply chain from the ground up. That doesn't mean Tesla intends to manufacture every single component itself. The company will still rely heavily on major external suppliers, in areas where building in-house manufacturing capability quickly isn't realistic. Musk specifically highlighted Samsung and TSMC as two of the most important partners here, both investing tens of billions of dollars into new semiconductor fabrication capacity, a portion of which could be allocated to support Tesla's broader AI initiatives, including both Robotaxi and Optimus programs. Micron was also called out specifically as a critical memory supplier, having allocated a substantial supply to Teslas on relatively favorable terms, even as Musk described current memory prices as exceptionally high across the industry. This underscores an important strategic point. Tesla isn't developing Optimus as a standalone robotics side project. It's positioning the robot within the exact same AI computing ecosystem that powers full self-driving, the Robotaxi network, and Tesla's broader AI model development, all of which depend on the same underlying advanced AI chips, memory, and ultra-low latency control systems. That means a shortage of AI chips wouldn't just slow down Optimus training, it could directly constrain how many physical robots Tesla is able to manufacture at all, since these different programs are all competing internally for the same limited hardware resources. Looking ahead, Optimus Gen 4 is expected to move production to Tesla's Austin facility, incorporating what Tesla describes as more manufacturing-friendly components and a higher percentage of in-house produced parts. That shift matters enormously in mass manufacturing, because a design that performs well in a lab or demo isn't automatically a design that can be produced efficiently at scale. If a robotic hand requires too many manual assembly steps, or if every unit needs dozens of hours of calibration after leaving the line, Tesla simply won't be able to produce Optimus in high volumes at an affordable cost. Gen 4 doesn't just need to be smarter than Gen 3. It needs to be genuinely easier and faster to build.